Hi there, and welcome to Telefunken. In today's video, we're going to be repairing a RANE VP-12 Voice Processor. The VP-12 is a multifunction processor that, as the name might imply, has a number of distinct processing units that have been designed specifically to affect vocal signals. The RANE has selectable line level and microphone level inputs and includes a source of 48-volt phantom power to provide power to condenser microphones. It has a microphone gain function configured to provide up to 60 dB gain. From there, the signal passes through a selectable, adjustable, high-pass and low-pass filter, allowing for the removal of both subsonic rumble and supersonic frequencies beyond those found in the human voice. The next section is a de-esser, which allows the user to selectively attenuate sibilant sounds. Sound then passes to a selectable combined gate expander compressor section. This can be used to remove noise from quiet passages by adjusting the noise floor or threshold and to compress the dynamic range of the signal, thereby reducing the volume of louder passages. The compressor is followed by two bands of parametric EQ with frequency, level, and what's labeled BW for bandwidth, what most of us might think of as Q. The output section has both a main and auxiliary output with helpful level meters, and the output level is switchable between line level and microphone level output. This unit is not considered to be particularly high-end, but it has been described as being very well suited to processing voiceovers in the broadcast setting, which is perfect because I intend to use it in my own studio for recording voiceovers in videos like this one for YouTube. I purchased this in non-working condition, so we're going to examine it and see if we can get it working again. Spoiler alert, you're listening to it right now. Okay, what we have on the bench here is a RANE VP-12 Voice Processor. And this unit, which barely fits in the camera, is a one-unit rack-mounted vocal processor, as the name might imply. So this thing doesn't work currently. The way that it's been described to me is that it works fine until you engage the de-esser and or the gate expander compressor. So the low cut, high cut filter sections and the parametric EQ and the mic preamp are all working, but both the de-esser and the compressor are failing in various ways. And this could be the result of some hard use that this piece of equipment has seen that I'll describe in a little bit more detail. If we do a quick visual inspection, we see that over here it has a power supply section with quite a bit of filtering on the power supply. The power comes in through this connector here, which is very similar to an RJ45 connector that you'd use for Ethernet. And the power is provided by a wall wart that provides approximately 18 volts center tapped through this connector of AC power. It's then rectified and filtered and regulated. We see a whole lot of op amps, but we also see a few specialized chips. We see this SSM 2164, which is if I recall correctly, it's a VCA chip. And we see two that audio chips. And I believe these are RMS amplitude detectors. And these will be used in both the de-esser and the compressor sections. A quick visual inspection reveals that most of the capacitors appear to be more or less okay. There's a fair number of electrolytic capacitors in this equipment. They appear to be okay with the possible exception of one that seems to be bulging a little bit, and that's this guy over here. So we'll figure out what it's doing and see how it's performing. I've got the lid off of it, obviously, and I've got the bottom off of it, which you can't see right now. But one of the nice things about this piece of gear is that both the top and the bottom come off. And that gives us access to both sides of the circuit board, which is kind of nice. It's a single-sided circuit board, so really pretty easy to work on compared to some. The single-sided nature of the board has necessitated all of these jumper wires that you see throughout. But the nice thing is the jumper wires are only going in one direction. The layout seems pretty logical, so on and so forth. It's got these two daughter boards. These are to house the circuitry that drives the meters on the front section here. It was missing part of one knob. There's a knob here that controls both the main and auxiliary output level, and the knob for the main output was missing, and I've temporarily put one of these guys on here. It has a number of these little micro switches, and one in particular that drives the phantom power is damaged on the back, and I'll show you that in a little bit more detail in just a moment. But before I go there, I thought I might set this thing up and put some audio through it. So first things first, I'm going to have to put some power into it. I have the power brick plugged into the variac, and the variac is on. I will plug in the power connector, and you might have heard a little click. I have the line inputs selected, and I've connected a cell phone with the function generator app, and we can listen to that. And we can use this to determine whether or not the various sections are working. So I'll turn that down a little bit. But if I connect the de-esser, we see that we lose all of our signal. So that's shutting everything off. And if I connect the compressor, we've lost everything. And then gradually we hear kind of a noisy signal. So that's our sine wave. And then when we connect the compressor, we hear this, which sounds a little bit more like a square wave perhaps, or distorted sine wave. And that's not due to any kind of overdriving of the system. The level is quite low at the moment, but something in the gate expander compressor section is distorting the signal. So I mentioned that this piece of equipment had a hard life, and I'll show you a little bit about what I mean by that. If we examine the back of this equipment, we can see these three terminal blocks. And these are used for both input and output. Input over here, output over here. And also to allow for patching in and out either sidechain for the compressor or inserting other processors in between the various elements of this multiprocessor unit. What's not really obvious just glancing at it is that in spite of the fact that this terminal block is pretty secure, these two terminal blocks here are actually not secure at all. And in fact, it appears as if the equipment has been dropped or something, because this terminal block's actually got a piece of plastic that is broken off of it. As well, if we look at the phantom power switch, which is over on the back right-hand side, the switch is, well, I can't even push it in and out. And that's because the switch has been damaged. So it looks like it was dropped on its back or on a corner. And these terminal blocks have actually broken right off the printed circuit board on the inside of the equipment. What makes this additionally concerning is that the signal actually goes through these terminal strips here. In fact, these little bridge elements are part of the actual signal path. And so if there are poor connections anywhere, but in particular along here, that could be contributing to the phenomena that we've observed with the poor performance. First things first, I think we need to do a little bit of physical repair, repairing these terminal blocks, making sure that they're connected properly, replacing this phantom power switch, and we'll do some inspections of the power supply, the various electrolytic capacitors and the like, and ensure that they're all within specification before we do anything else in an attempt to diagnose what's going on with this gear. I'll move the camera a little bit and hopefully show you a little bit better view of what's going on with the phantom power switch. So this is the phantom power switch that is damaged, and you may or may not be able to really tell that it's damaged, but we'll compare it to one over here that's intact and is functioning properly, as opposed to this, which if I push on this, it's almost coming right off of the board. In fact, it seems hardly attached to the board. So we'll have to figure out what's going on there. So after removing all the screws from the back panel, taking these jumpers off and then reattaching them where they belong, and taking the screws out of the front panel, I'm able to take this part of the chassis off of the equipment. And what that does is it gives us access to both sides of the circuit board, as you can see. But it also allows us to work on this with the faceplate on the equipment, which can be kind of helpful, I find, because it's nothing worse than trying to diagnose what's going on with equipment when you've lost the labels on the front and you can't tell which potentiometer you're adjusting or where it might be adjusted in its range. If need be, we can take this front faceplate off, but we don't need to for the time being. So we'll again turn our attention to some of the damaged bits. And for example, you can see that this terminal block is just floating in the breeze. All of the solder joints are broken right off, as is this one. Now this one appears to have been resoldered, but whether or not that was done well or not remains to be seen. This jack has been resoldered as well. And the reason I can tell that is because there's a bit of solder flux, which is evident here on this part of the board. So I have resoldered all of these connectors to the printed circuit board. I've replaced the phantom power switch, and I've replaced this bulging 10 microfarad capacitor. And I now have the processor attached to a signal generator and an amplifier. It's sending a 1 kilohertz tone. And we can turn that down. We don't need to listen to it, but this is passing through the instrument, but a couple of the sections are in bypass mode. In particular, the de-ess. If I take it out of bypass, we don't get any signal. And the compressor. If I take it out of bypass, we get a signal, but the signal is quite distorted. The EQ works just fine. And I can use that to change the intensity of the 1 kilohertz tone, but I'll just stick that in bypass as well. Actually, I'll leave it in. If we turn that down, we can probe with an oscilloscope at various points along this rear connector. And in particular, if we probe this point here, this is what's referred to as the preprocessor out. This is the de-esser in. And we see both these points, we have a perfect sine wave. If we go to the de-esser out, we see that we have a sine wave, but it has a DC offset. So this sine wave has a DC offset of about 8 volts, which it should not have. The signal that comes from the de-esser out passes through a 22 microfarad non-polarized capacitor before it reaches this point on the PCB. No surprise, the compressor in, we see the same signal because it's really just passed from this terminal point to this terminal point through this jumper here. And then at the output of the compressor, we see that we have a perfectly fine sine wave. However, this is with the compressor bypassed. If we take the de-esser off bypass, we get no signal at the de-esser out. And if we take the compressor out of bypass, we see that there's no change to the signal going into the compressor. However, the signal coming out of the compressor sounds terrible. So this is with the compressor bypassed, we have a perfect sine wave. And with the compressor engaged, we see a very distorted signal where one half of that sine wave is flattened off into a square wave, essentially. So that gives us some hints as to what might be going on with this processor. We can consider, for example, which elements on the printed circuit board are common to both the de-esser and the compressor. And we see that this integrated circuit, Z8, is indeed common to both. So that could be a problem. However, the type of problem that's manifesting is different between each section. They're not manifesting the exact same syndrome. Nonetheless, given that this integrated circuit here is socketed, it's quite tempting to just pull it out and replace it and see what that does for us. So I think I might set about to do that right away. Let's have a quick look at the schematics for this equipment and see if what I've just proposed makes sense. This is the schematic for the de-esser circuit. This circuit uses those unusual chips I'd mentioned earlier, the THAT2252 and the SSM2164. If we examine the schematic, we can see that the audio signal passes through the SSM2164, but that the THAT2252 is used in a feedback topology to provide a signal to control the SSM2164. The 2252 is an RMS level detector that's used to convert the AC current associated with the audio signal to a DC voltage that's used to control the SSM2164, a voltage-controlled amplifier. We hope that there's nothing wrong with this chip because they're obsolete and somewhat hard to find. The THAT2252s that I have on hand were purchased off eBay, not currently among my list of qualified reputable vendors. The 2252 chip was used in many different audio devices in the 90s, including the ubiquitous Alesis 3630 compressor, favored by those chasing that pumping sidechain sound made famous by purveyors of French house such as Daft Punk. In our circuit, the DC signal produced by the 2252 passes to the 2164, another obsolete device. The SSM2162 is a quad voltage-controlled amplifier, originally made by SSM, a company formed by members of the Silicon Valley-based Homebrew Computer Club that also spawned Apple. SSM assets were acquired by Analog Devices in 1990, and they continue to produce chips with SSM badging. However, the 2164 is not among them. However, all is not lost. Alpha, Cool Audio, and Sound Semiconductor all have come out with their own versions of this chip, and I happen to be in possession of 2164s from both Alpha and Cool Audio. They can be obtained easily from the Modular Synth community, and I obtained mine from Modular Addict. The function of the 2164 in our circuit is to respond to the conditioned and processed DC signal from the 2252 RMS peak detector and turn down the VCA whenever it detects a sibilant signal. Those of you with a keen eye may have noticed something a little odd about this schematic, at least it seems off to me. Highlighted in red are 3 op-amps, housed in IC6, a TLO74. The rest of this device contains much more modern op-amps with much higher specs, such as 2059s, 4574s, or 5534s. Why have RANE elected to use the somewhat long-in-the-tooth TLO74s in the audio path in this device? Is it due to their FET-coupled inputs and outputs? If you have any ideas, please put them in the comments below. The rest of our 2164 and the other 2252 are used in the compressor part of the device. In this case, we have an example of a feed-forward topology, in which a portion of the input signal presented to the VCA is fed to the 2252 peak detector. Signals that are deemed too hot, depending on the user's settings, are translated into a DC signal that tells the VCA to reduce the gain and thereby level the signal. For what it's worth, there are no TLO74s used in this part of the circuit, but instead, the audio signal passes through op-amps in Z9, a 2059 quad op-amp, but with BJT coupled inputs and a FET coupled output. The fact that the 2164 is the only piece of silicon common to both the de-esser and the compressor audio paths makes it a likely suspect. So let's see if replacing it fixes our problem. First I'll ground myself to the board. Bend these pins in slightly. Okay, so we can hear this with the de-esser disengaged. And now we have the de-esser engaged. We can still hear it, whereas before we could not. And now we have again, what appears to be a pure sine wave. Sine wave, sine wave. So we have a reduced signal outgoing, and this is the compressor out. We turn the compressor ratio down, we regain our signal, and we appear to have a clean signal all the way through. And that's with all of the sections engaged. So replacing this one chip, which was common to the circuit, seems to have gotten the processor back in working condition. All that remains really now is for me to examine it and examine its performance and make sure that the rest of the components are working as they should. So for example, I'll check the ESR on all the various capacitors. I'll check all the potentiometers and make sure that none of them are particularly scratchy. I don't want to be cleaning these just for the sake of cleaning them because they're packed with grease, which makes their travel nice and smooth. And once I start spraying deoxit or anything else inside these, that's going to change things. But nonetheless, it seems we have some success here. After checking the rest of the VP-12, I found that everything was working properly and that the repair was complete. I considered undertaking a recap and replacing the electrolytic capacitors in the power supply, as well as the 18 or more non-polarized 22 microfarad electrolytic capacitors in the audio path. In the first case, I noted that this piece of gear does not have a power switch, so the capacitors in the power supply section are going to be in use as long as the device is plugged in, which is probably most of the time. Call me lazy, but until I'm sure I like this unit and want to keep it, I've elected to install a power switch in the power cord for the wall ward to ensure that the power supply is stressed only when the device is in use. With respect to the non-polarized caps, I've checked their ESR and they all seem within specification. I don't recognize their branding, but again, I might take a wait-and-see approach before replacing them with non-polar Nichicon Muse or something similar. Tell me what you think in the comments below. That's all for today's video. I hope you've enjoyed it. If so, please check out the other videos on my channel and consider subscribing. And as always, thanks for watching.